Let's look at the definition and some examples of series in this lecture. Do you believe that we could express a number as an infinite sum? Here's an example. I can express pi over 4 as the following, as 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus 1 over 9, and that goes on forever. So I'm alternating between the sign, and from the term to the next term, it is 1 over an odd integer. You could try it out with your calculator. As you add more terms, the answer will get closer and closer to pi over 4. So that's what we'll be learning in this section. As we finish section 3 and section 4, you'll also be able to express a value as an infinite sum. So as I mentioned in the overview of this section, a series is the sum of an infinite sequence. The sequence has terms an for n equals to 1 to infinity. Then we get an expression of the form a1 plus a2 plus a3, and that keeps going until infinity. So it is similar to an infinite sequence, but instead of each terms, now we add them up. We can also denote the series by the symbol, the sigma symbol that we learned in Calculus 2. So we can also write that as sigma for n starting from 1 to infinity, and the terms are an. Or just by short, similar to the sequence, we can simply write that as sigma of an. So when we don't write out the initial value, n equals to a value, then we are assuming that the series starts when n equals to 1 and that goes to infinity. Let's look at the first example. Here we have sum of I, for I equals to 1 to n. So the first term will be when I equals to 1, that is 1, plus the second term is when I equals to 2. So plus 2, and third term is 3, and we add all the terms until we get to n. And this also equals to n times n plus 1 divided by 2. So that's what we learned from Calculus 2. How about if we have an infinite sum? So instead of adding to n, now we add all the numbers when n goes to infinity. Then if we expand this sum, that is 1 plus 2 plus 3, and then plus n, and that keeps going forever. But if we keep adding values, you'll note that this series will go to infinity. How about this example? Here we have sum of 1 over 2 to the power of n. So the first term will be when n equals to 1, that is 1 over 2. Then plus, the second term is when n equals to 2. So we have 1 over 2 to the power of 2, that is 4. And the third term would be 1 over 8. Then plus, the fourth term is 1 over 16. So we add all the terms up. The nth term would be 1 over 2 to the power of n. And we continue adding all the terms until n reaches to infinity. And as we'll learn later in this section, this series will converge to 1. So from the first two examples, we already see that some of the series could converge to a finite value, and some of them, when we add up all the terms, that will give us an infinity. So how can we conclude whether a series is convergent or divergent? Then we'll need to define the term, the partial sum. A series is a sum of infinite terms, and partial sum would be part of a series. So we define S1 as only the first term, A1. And S2 is the partial sum with only two terms, so A1 plus A2. Then S3 would be sum of the first three terms, A1 plus A2 plus A3. So similarly, if we have Sn, then that would be the sum of the first n terms, A1 plus A2 plus A3 plus until we get to an. Or we can denote that as sigma for I equals to 1 until n of ai. So the actual sum of this series, S, which is the sum of an for n equals to 1 to infinity. So a sum of infinite terms. This also equals to the limit as n approaches to infinity of the partial sum, Sn. Here's a summary of the terms that I just mentioned. Given an infinite series, a1 plus a2 plus a3 until forever, so we have infinite terms. Then we denote Sn as nth partial sum. So Sn would be the sum of n terms, a1 plus a2 until plus an. Then we can define the partial sum as a sequence. So the sequence would be the partial sum S1, S2, S3. So that is a sequence. Then, if the limit of this sequence converges, which is the limit as n approaches to infinity of the nth partial sum, then that means the series converges, because the limit of Sn, the nth partial sum, by the definition, that equals to the sum of the series. So if this limit exists, then we call the series sum of an is a convergent series. So we have an infinite sum here, and this equals to S, which also equals to the limit as n approaches infinity of the nth partial sum. So this S also equals to the limit as n approaches to infinity of the partial sum for I equals to 1 to n of ai, which also equals to limit as n approaches to infinity of the nth partial sum, Sn. So this S, we also call that the sum of the series. But if the sequence for the partial sum is divergent, then the series is called divergent. Let's look at this example. Suppose the partial sum of a series is given. Sn is a1 plus a2 until plus an, and the form is given. It is 2n divided by 3n plus 5. Then by the definition, the sum of the series would be the limit of the partial sum. So we could find the sum of the series by taking the limit of this Sn. So the sum of the series, S, equals limit as n approaches infinity of Sn, which is limit as n approaches infinity of the form given in the problem, 2n divided by 3n plus 5. We can factor out the n in the numerator and the denominator, and we'll find that this limit equals to 2 over 3. And that is the end of the lecture. In the next lecture, we are going to look at a special series called the geometric series. In some cases, it is possible to find the finite sum of a geometric series.